Okay, hello everyone. Okay, I think good afternoon. We'll start with today's quote. If you want something you have never had, then you have got to do something you have never done. Okay, so if you are living as it is, you get the things as it is, right? There will not be any change in your life. If you want some change or if you want to achieve something, then you have to do some things which you are not doing regularly. If you want something extra, you have to do something extra. So if you lead a normal life, your things, everything will be normal only, right? If you want to do something different, get something different, you have to do something different. And today is the birthday of James Watt. I think everybody knows about him. He's so popular. And he is the man mainly responsible for industrial revolution. And the steam engine is the one which completely changed the scenario of the world. So he's a Scottish engineer and inventor whose steam engine contributed substantially to the Industrial Revolution. In 1763, he repaired the model of Newcomen's steam engine. First steam engine is devised by Newcomen, belonging to Glasgow University, and began experiments on properties of steam. The Newcomen engine was simple in design. It acted as a pump, and a jet of cold water was used to condense the steam. But what improved on this design by adding a separate condenser and a system of valves to make the piston return to the top of the cylinder after descending. He took out a patent for a separate condenser in 1769, and he later adapted the engine to rotary motion, making it suitable for a variety of industrial purposes, and invented flywheel, governor. So many inventions he has done, whatever is needed for the steam engine. So his contribution is very heavy, and as I told, the industrial revolution came because of the steam engine, and he is responsible for that. Okay, today we will discuss about the practical Brayton cycles. Okay, and just we will quickly revise what we have done for the ideal cycles. So we have discussed about 8 cycles. One is simple cycle. So you can see that only compressor, turbine, and combustion chamber, and here the power generator will be there this side. And we have this PV diagram and TS diagram, and we have the efficiencies. We have developed the relations for non-dimensional work and efficiency. And we have defined 2 parameters. One is T, which is the ratio of the highest maximum temperature and minimum temperature, T03 by T0, or T3 by T1. And C is the pressure ratio to the power of gamma minus 1 by gamma. So we get this is the non-dimensional turbine work, this is non-dimensional compressor work, and we get this efficiency. And efficiency is a function of the pressure ratio and gamma. So you can see that pressure efficiency increases with pressure ratio and also with gamma. And compare it, coming to work, we have seen that it increases and decreases. So 0 to 0, and we have optimum in between. And the optimum C is found to be root T. And we have seen heat exchange cycle then, because whenever the pressure ratio is less, then there will be more difference in temperature of T4 and T2, and more heat will be lost. So if you want to recover that, we will provide a heat exchanger so that the exhaust gases from the turbine will be used to heat the compressed air from the compressor. So the amount of heat supplied can be reduced. So if I do like that, then the net output will not change, but efficiency will be changed, 1 minus C by T. And the maximum efficiency, it starts from Carnot efficiency. And as C increase, it gradually decrease and reach the simple cycle efficiency. Okay, that's what we have seen. And then we have discussed about the reheat cycle. So in between the turbines, we can have further reheating. So why? Because I have metallurgical limit, I cannot increase the efficiency very much because there is a limit for the maximum temperature. If I can expand in first turbine, and then if I can reheat it further, so my input can be increased and the output also can be increased. So here you can see that the area of the diagram increases, so the net output increases. So that's what we have seen. Though the graphs look similar to simple cycle, the quantitatively the values will be higher. But it is at the loss of efficiency. We have seen that we are adding another small Brayton cycle of low pressure ratio, which will have low efficiency. So the efficiency will be somewhat less. If I take this as simple cycle efficiency, and as T increase, if T is small, the efficiency is very low compared to this. But as T increase, it tries to approach the simple cycle efficiency. And if I want to have higher efficiency, then what should I do? I have to put heat exchanger. So if I put heat exchanger with the reheater, so here I add this after the second turbine, if I put it heat exchanger where it loses heat to the compressed air, so I will have a lot of reduction in the heat input. So now you can see that again, the efficiency curves come like this. Similarly, you can have intercooler between two compressors. You can have an intercooler, and we have done the derivations, and intercooler with heat exchanger, then intercooler and reheater if you have. So this is the schematic PV diagram, TS diagram, and output and efficiency, and with all of them. So these 8 cycles we have discussed, and I asked you to calculate, okay, for a given value of pressure ratio 4 and T3 by T1 is 6. And have you done this?
Yes, sir.
Yes, sir. Somehow I tried.
Can you tell me the values of simple cycle? What is the work and efficiency? Anybody efficiency how much?
Just a minute. So 0.327.
Yeah, 0.327, right.
So I got 0.38, I think.
Okay, so okay, this is the way you will get. Okay, these are just, we have to substitute in the formula only, because R equal to 4, R power gamma minus 1 by gamma, gamma minus 1 by gamma is 0.2857. So 4 to the power of 2.857, you will get this 0.2857, you will get this 1.486, and T equal to 6. Just to use these two, okay, C and T, you will get this output, input, and efficiency. Okay, you can see that efficiency of a simple cycle is 32.7, and heat exchange cycle, it is 75%. You can see such a large increase. Why it is so much? Because of low pressure ratio. If the pressure ratio is less, okay, so what happens? There will be more loss in the heat from the exhaust. So if it can be recovered, so I can increase the efficiency up to 75%.
Sir, is it due to pressure ratio or heat input?
No, it is due to heat exchanger. I am recovering a lot of heat. Work output is not changed. Okay, work output will be same. Is it clear? Because of low pressure ratio, T4 will be very large. T2 will be less and T4 will be large, and there will be more difference in T4 and T2. So I can recover more heat from the exhaust. Because of that, I can reduce the heat input very much. You can see just 1.9623 instead of 4.514. Work is same.
Okay, sir.
Okay, so because of that, so much increase in the efficiency I get. Okay, now if I have intercooler, what will it do? It will reduce the compressor work, and so net work will increase. From 1.4763, it became 1.5243. Right? But input will increase because compressor output is, because of the intercooler, compressor outlet temperature will be less. So T minus root C, if you remember, the heat input will be T minus root C. So it will be more than 4.514. And because of that, intercooler reduces the efficiency from 0.327 to 0.319 or 31.9%. Am I clear about it?
Yes, sir.
So again, if I have heat exchanger, I can have more than 75.2, it is 77.7% I will get. Because the difference between T4 and T2 further increases because of the intercooler. Okay, then if I have reheater, I have large increase in the output because of the reheater, and large increase in the input also, and more decrease in the efficiency, 29.9. But if I add heat exchanger also to this, right, so I will have 74.6%. Okay, and if I have intercooler and reheater, both of them decreases the input, increases the output, and decreases the efficiency. It comes to 29.3. But if I have heat exchanger, intercooler, reheater, heat exchanger, then I will have the maximum efficiency, almost 80%. Right, you can see that it is almost 80%. Okay, what is the Carnot efficiency for this T? 1 minus 1 by T is the Carnot efficiency, right? So minus 1 by 6. That is 5 by 6. So how much it comes to?
83%, sir.
So you can have almost very near to Carnot efficiency. You can see if I have all of them. But only thing is, it increases the complexity. It increases the cost very much. Sir. This heat exchanger, reheater, they are huge. Heat exchanger means it is a, if I want to have a perfect heat exchanger, it should be very, very large. Okay, so whatever heat is lost by exhaust gases, if everything is to be taken by the air, it should be very huge equipment. And there will be pressure losses also if it is large during the piping and all, because these are ideal things. I am getting so high values, but in reality, I will not get this many high values. We will see in reality what happens. Okay, actually, I asked you to write program also. Anybody tried MATLAB code?
Yes, sir.
Could you get
Yes,
anything?
sir. All the graphs.
Okay. Can you share and show?
Yes, sir, sure. Just a minute.
You are
Sir Shubhankar Sinha.
Shubhankar. Okay. Okay. Anyway, we will discuss later first because I don't want to lose time.
Okay, sir.
I will show my code. Okay. So this is the code I have written. It's a small code only because all cycles are included in the same program. I have written like this. So you can see, suppose a simple cycle, I can T into 1 minus 1 by C minus C minus 1 is the output. T minus C is the heat, and efficiency work by heat. Just like that, simple formula. And when you come to heat exchange cycle, okay, this heat will be 1 T into 1 minus 1 by C for heat exchange cycle. Suppose if you come to intercooler, 2 into root C minus 1 is the compressor work. Okay, so just a substitute of the program code will be same for each cycle, but only this formula can be changed. Okay, just I will show you. If I execute, it is asking the number to which cycle you want, like that. If I take simple cycle 1, enter, it will give the plots. Okay, this is the work output plots, and this is only one single line for efficiency. Okay, so it increases and decreases like this. Okay, this is for simple cycle. And if I take 2 heat exchange cycle, so you can see that from Carnot efficiency, it decreases. I didn't draw the simple cycle here, so it comes and stops somewhere here. The R is increased up to 30. Okay, so this work will be again increasing and decreasing only. And so you cannot distinguish because values are not there, legends also are not given. You cannot distinguish, but the cause comes almost similar things. Okay, this is for intercooling cycle. So you can see the efficiency for T is equal to 3, it is like this. So 4, 5, 6, 7, 8, like that. If I increase small t, it approaches the simple cycle efficiency. Okay. Okay, this is the way we can write the code. Okay, and I will give you some tips to remember the formulae, right? I'll just tell you how simple it is. And suppose I take simple cycle. So we have defined P is equal to R is equal to P2 by P1, and C is equal to R to the power of gamma minus 1 by gamma. So small t is equal to T3 by T1. And so if I can get, so C is also equal to T2 by T1, because T2 by T1 is P2 by P1 to the power of gamma minus 1 by gamma, or R power gamma minus 1 by gamma. C is equal to T2 by T1. And also this is equal to T3 by T4. Is it okay? Now what I do is, I will, because I want T1 by T1, T2 by T1, T3 by T1, T4 by T1 like that. So this, for T1 by T1 is 1, T2 by T1 is C, T3 by T1 is small t, and T4 by T1 is equal to T4 by T3 into T3 by T1. Okay, so T by C, like this. So now compressor work is C minus 1. T2 minus T1 is C minus 1. Compressor work, non-dimensional compressor work is C minus 1. And non-dimensional turbine work is T minus T by C. T3 minus T4, right? So T into 1 minus 1 by C. Like this you can get. So W net is nothing but T into 1 minus 1 by C minus C minus 1. And what about Q by C by T1? So this is T3 minus T2. T3 is T and T2 is small c. Okay, like this. So efficiency is Wn by Q. Am I clear about it?
Yes, sir.
Okay, suppose okay. If I come to heat exchange cycle, so this so heat exchange cycle, because T5 equal to T4, Q will be equal to T3 minus T5. Okay, so this is small t by C, so this is also t by C. T5 also t by C. So it is T minus T by C, or T into 1 minus 1 by C for heat exchange cycle. Output will be same, input will change like this, because turbine work is equal to heat addition. This is turbine work T3 minus T4, and heat input also T3 minus T4, T5, which is equal to T3 minus T4. Am I clear?
Yes, sir.
Yes, sir.
Yeah. Now if I take intercooler cycle, I will put 2 here. Okay, this is 1. And what is this point? T5 by T1 will be root C. Am I right? C1 or root C. And T6 is again T1 only. And these two will be same. So this is also root C. And this is small t, this is T by C. Okay, so compressor work, here root C minus 1, root C minus 1. 2 into root C minus 1. And W turbine, T into 1 minus 1 by C. And W net, T into 1 minus 1 by C minus 2 into root c minus 1. And what is heat input? T3 minus T2 dash, okay, up to here. So this is T and this is root c. T minus root c. Like this. This is intercooling cycle. If I keep IC plus HE, so what happens? So this will become like this, this will become like this. Up to here, I have to give input. So I will put some 7 here, 8 here. So this is the input I will get. So Q is equal to T3 minus T7, which is T minus, because this is T by C now, same as this. Okay, so T into 1 minus. This is the only thing gets changed. So efficiency again Wn by Q. And similarly, if I come to reheat cycle, so this is 1, 2, 3, 4, 5, 6, something like this. So this is 1, this is C, and this is small t, and these two are same. This is also small t. And what will this become? Actually, these two will be same. Okay, if I draw it right, okay, I will draw it better way. Because these two should come same, these two should come same, because pressure ratios are same. Okay, so this is 1, this is C, this is T, this is T, this is T by root C. Instead of C, it will be T by root C, because T by C1, T by C2, like this. So WC is equal to C minus 1, WT is equal to 2 into T into 1 minus 1 by root C. W net is equal to 2T into 1 minus 1 by root C minus C minus 1. And the efficiency is equal to, and Q is equal to, in the first heat exchanger, T minus C, first combustion chamber. And in the reheater, how much? T minus T by root C. Like this. Okay. And if I have reheater plus heat exchanger, so this will be like this will be like this can be 7 and this can be 8. So only Q will change, and Q is equal to T3 minus T7 plus T6 minus T5, and T3 minus T7 is first turbine work, and T6 minus T5 is second turbine work. So it will be equal to turbine work, like this. And again you get W1 by Q. And if I take intercooler plus reheater, these two will be at the same temperature. These two will be at the same temperature. These two will be like this. If I put like this is 1, this is root C, this is 1, this is root C, this is T, this is T, this is T by root C, this is T by root C. Okay, so WC is equal to 2 into root C minus 1, WT is equal to 2T into 1 minus 1 by root C, and W net is equal to WT minus WC, and Q is equal to T minus root C in the combustion chamber, and T minus
T by root C.
plus okay, plus
T into
yeah.
plus T into 1 minus root C.
Yeah, plus T into 1 minus 1 by root C. Okay, so efficiency is equal to WM. And if I have interpolar, reheater plus heat exchanger, so then this will become like this, this will become like this if I put 9 and 10. So combustion chamber heat input is equal to first turbine output, reheater input is equal to second turbine output. So Q is equal to 2T into 1 by root C. So efficiency is equal to WM. Right? Like this, we can get all the things. Okay, it is easy to, if I just understand this, yes.
So T5, it will be equal to T10.
Yeah, T2, T5, T10, these are same. It is turbine exit temperature. It is going to out. And this is like heat exchanger, right? If I have heat exchanger, the exhaust gases come and leave, and it enters at 4 and leaves at 10. Compressor gases, air will come at 2 and leaves at 9. So T9 equal to T7 equal to T4, T2 equal to T5 equal to T10. So this is the heat that is lost to the surroundings. This heat is recovered. Is
Yes,
that
sir.
clear? Is it okay?
Yes, sir. Yes.
Yeah. Okay, these are real cycle or ideal cycles. So then we have to go for real cycles or practical cycles. So for A standard cycles, we have made lot of assumptions. So I will try to implement the effect of that, whichever is possible. Okay, but not complete real cycle we cannot analyze, right? We will try to approach it. That's all. Okay, the first one, we have assumed A to be perfect gas. Okay, but air is not a perfect gas. So how to give the real gas effects to that? So here, as long as it is compressed, it is air only. Okay, so as long as it is air, Cp of air is 1.005 kilojoule per kg Kelvin, and gamma of air is 1.4.
1.4.
Okay, but as temperature rise, do you know what happens to Cp?
Increases.
Increases. It increases like this. And what happens to efficiency, the gamma?
Increase.
Okay, actually, who told decreases?
That's Mount to South, sir.
Sahu. So why it decreases, but Cp is increasing, no?
Actually, I thought I know for gas we are using 1.33.
Yeah.
So that's
Yeah,
why
that's
I remember that
what
one.
happens is,
So CV also increases.
yeah, because C with as T increase,
CP and CV both increase.
CV also increase, but increase in CV is greater than increase in Cp. Okay, because gamma is Cp by Cv. Cp increase, Cv increase, but Cv increases more. Therefore, gamma decreases. Is it clear?
Yes, sir.
So actually, if I draw gamma value, it comes like this. Gamma decreases. So for gases, exhaust gases, Cpg is taken to be 1.147 or 8. And gamma G as 1.333. So to introduce the effect of real gas, so what we do is we will take these two values as long as it is air, and take these two values when it becomes gases. Okay, so what I do is, suppose if I want compressor work, Okay, so m dot into Cp into T2 minus T1, right? So instead of that, I have to put m dot Cpa into T2 minus T1 because it is air only. But when I take turbine, m dot T3 minus T4, I have to put Cpg. Is it clear?
Yes, sir.
Similarly, if I take Q, m dot Cpg into T3 minus T2. Like this, I have to write. In combustion chamber and turbine, I have to use Cp of gas. In compressor, I have to use Cp of air. Similarly, suppose if I use heat exchanger, right? Heat lost by exhaust gases is equal to heat gained by something like. So I have to use Cpa for air and Cpg for gas. Is it clear? So if this is heat exchanger, if it is going with TA1 air and it is going with TA2 and it is entering gases as Tg1, suppose just like that, Tg2 it is like this. So heat gained by air is m dot Cpa into TA2 minus TA1 is equal to m dot Cpg into Tg1 minus Tg2. Is that clear? Is it clear?
Yes, sir.
Yes, sir.
Okay. Similarly, if I take suppose T2 by T1 is equal to P2 by P1 to the power of gamma minus 1 by gamma for compressor, right? So here I have to put gamma A minus 1 by gamma A. If I put for turbine, T3 by T4 is equal to P3 by P4 to the power of gamma minus 1 by gamma, I have to put gamma G minus 1 by gamma G. Am I clear?
Yes, sir.
Yes, sir.
This is the way I have to implement the effects of variation of Cp and gamma and get the real gas effects. Okay, this is the first one. So the second one is effect of change in kinetic energy in all the components. So I want to get the change in kinetic energy because we know that Q is equal to or delta Q is equal to dH plus d of Ke plus d of Pe plus delta W, right? First one. Okay, d of Pe is very small because it enters and leaves all the components at the same level. So this is negligible. But d of kinetic energy, because there is compression in the compressor and the expansion in the turbine, there is a lot of change in the velocity is coming. So if I want to implement the effect of kinetic energy, okay, how to do about it? Okay, this is like Q12 is equal to H2 minus H1 plus C2 square minus C1 square by 2 plus delta W. So what I do is here I will write it as H2 plus C2 square by 2 minus H1 plus C1 square by 2 plus delta. And this enthalpy plus kinetic energy, this is called as stagnation enthalpy. H naught is equal to H plus C square by 2. Right? You might have learnt in your compressible flow. And so what is this? How we define? Stagnation enthalpy is the enthalpy of the fluid when the fluid is brought to zero adiabatically.
Sir, isentropically or adiabatically?
For P naught, it is isentropically. For H naught and T naught, adiabatically. Is it clear? Because pressure, friction comes into picture there. There I have to do isentropically. But for H0 and T0, it is adiabatically. When the fluid is brought to rest adiabatically. Okay, this is important. For stagnation pressure, it is isentropically. Okay, so H0 is equal to H plus C square by 2. So what I can do is, I can write this as Q12 is equal to H02 minus H01 plus W12. Okay, this W. Or I'll write delta Q is equal to DH0 plus delta W. Like this.
So why P
Yes.
pressure for isentropically? So we can do one process at a time, no, sir? So if we go for adiabatically, then how we can write the pressure term? That
No, actually P0 is equal to P plus C square by 2. That is for Bernoulli's equation we get. So there it is assumed to be no friction is there. But here we don't assume anything. Is it clear?
okay, sir.
That's right. Okay, H0 is equal to CPT0. And actually here you can get the gas dynamic relation like CPT0 is equal to H plus C square by 2. So CPT plus C square by 2. And T0 is equal to T plus C square by 2 CP. And CP is gamma R by gamma minus 1. CV is R by gamma minus 1. So if I substitute here T plus gamma minus 1 by 2, C square by gamma. If I take T0 by T is equal to 1 plus gamma minus 1 by 2 C square by gamma. Okay, so here the sonic velocity A square is defined as dP by d rho. For isentropic relation or adiabatic relation, it is gamma P by rho, which is equal to gamma RT. Okay, so this is 1 plus gamma minus 1 by 2 C square by A square, and Mach number is equal to C by A. So T0 by T is equal to 1 plus gamma minus 1 by 2 m square. Okay, this is the popular relation which we widely use in compressible flows. Okay, now I have to use delta Q is equal to DH naught plus delta W, not DH. If I
Sir?
use DH, yes.
Sir, this expression is valid for all the Mach numbers, like less than 1 or greater than 1, supersonic or subsonic.
Yeah, whatever it is, the formulas are same, whether it is subsonic or supersonic.
Sir, but when we go from subsonic to supersonic, there is some, can say, like losses takes place due to some, you can say, the
Shock.
formation of shock
You're
waves.
talking about shock or anything?
Yes, sir, shock waves.
Yeah, even if there is a shock, okay, even if there is a shock, even in shock flow, okay, suppose shock flow is there. Here delta W is 0. Suppose I have a flow is taking place, there is a shock. So there is no work and there is no heat. So DH0 is equal to constant, right? Across a shock, DH0 is constant and DT0 also is constant. And T0 is equal to constant. Sorry, DH0 is 0 and DT0 is 0, or T0 is equal to constant, H0 is equal to constant across a shock. There will not be change in the stagnation temperature and stagnation enthalpy, but stagnation pressure decrease because of the irreversibilities, because of the increase in the entropy.
Yes, sir. But I think the temperature also increases. Stagnation temperature may be constant. but,
Stagnation temperature constant. Across shock, velocity, Mach number decrease, velocity decrease, pressure increase, temperature increase, density increase.
yes, sir.
Is it clear?
Yes, sir.
This is for the shock, but T naught remain constant. Okay, so it doesn't matter as long as you talk about stagnation temperature, stagnation enthalpy, whether there is a shock or not, it doesn't matter, right? Okay, so here
So, but stagnation pressure also decreases, no?
stagnation pressure decrease.
Okay, sir. But enthalpy, stagnation enthalpy.
Whenever there is increase in the entropy, there will be decrease in the stagnation pressure.
Okay, sir.
That's why we define, when you talk about pressure, stagnation pressure is the pressure of the fluid when it is brought to rest isentropically.
Yes, sir.
Okay. Right. So here, delta Q or delta W, when you consider compressor, turbine and all, instead of DH, previously in ideal cycles, I'm using DH. But instead of DH, I have to use DH naught. Okay. So delta Q is equal to Cp dt naught plus delta W. Okay. So hereafter, what I have to do is W compressor if I want, if I have to write Cpa into T02 minus T01 like this. Stagnation temperatures I have to use. And Wt is equal to Cpg into T03 minus T04. And QH or heat added is equal to Cpg into T03 minus T02. Like this I have to use. Is it clear? So if I use stagnation temperatures in place of static temperatures, I am considering the change in kinetic energy also into the calculations. Am I clear about it?
Sir, why we are doing here for stagnation only?
What is that?
So why we are doing calculation for stagnation only?
Why we are bringing stagnation?
Yes.
That's what I am telling. So if I am taking static temperatures, I am neglecting the change in kinetic energy.
Yes, sir.
But if I consider stagnation temperatures, I am considering change in enthalpy and change in kinetic energy also together.
Yes, sir.
That's why I'm taking stagnation conditions. Okay?
Okay, sir.
Yeah, that's it. So this is the way. So I have to use all those formulae with static temperatures. I have to use stagnation temperatures instead. Okay, to consider the change in kinetic energy. Okay, this is the next thing. And another thing is pressure losses. Okay, before going to pressure losses, I will consider losses during compression and expansion. Okay, they are not isentropic in reality. Okay, so when you are on TS diagram, yes, it increases, right? You have to show S increases instead of vertical line. Okay, now if I take a compressor, if this is not 1, this is not 2. Instead of 1, 2, I will put not 1 and not 2. This is T, yes. This is constant pressure line, this is constant pressure line. So instead of going like this, it goes like this. I will put ideal one as not 2 dash, real one is not 2. Is it clear? There will be increase in the entropy. Instead of going straight, it goes inclined way. But I am compressing up to the required pressure ratio. But because of this, what happens is, previously I have this much of work. W ideal is equal to Cp into T02 dash minus T01. Like this. But now it is going from 1 to 2. W actual is equal to Cpa into T02 minus T01, which is more than W ideal. Because of friction and irreversibilities, right? So I have to supply more work. Am I clear?
Sir, in the second case, you are still assuming to be adiabatic or not?
What is that?
Adiabatic, sir.
Ideal one, if it is going isentropic, I have to give only this much of work.
No, sir, in the second case, you are neglecting adiabatic or still assuming to be adiabatic?
It is adiabatic only. Adiabatic with friction. That's why isentropic is reversible adiabatic. This is irreversible adiabatic.
Yes, sir.
Friction is there, but adiabatic only. Okay. So here, efficiency, compressor efficiency is defined as small by large. Okay, W ideal by W actual. That is T02 minus T01 by T02 dash minus T01. Okay, CPA gets cancelled. Okay, like this. And so here, sometimes the direct formula will be written. Delta T012, that is change in temperature in the compressor, is equal to T02 minus T01. Sorry. I think I have written wrong. T02 dash minus T01 by T02 minus T01. Am I right? Ideally is T02 dash. Okay, so T02 minus T01 is equal to, if I so T02 minus T01 is 1 by theta C into T02 dash minus T01. This is equal to T01, if I take common, T01 by eta C into T02 dash by T01 is, because it is isentropic relation, so R power gamma A minus 1 by gamma A minus 1, like this. And the compressor work is equal to CPA into delta T012. Delta T012 can be calculated. Okay, you can calculate independently. So what normally we do is T02 dash by T01 is equal to compressor pressure ratio to the power of gamma A minus 1 by gamma E, which gives me T02 dash. And then compressor efficiency is to be used, T02 dash minus T01 by T02 minus T01. In this, unknown is T02. This is to be calculated. Okay, always whenever you solve the Brayton cycle, I have to go from point to point and I have to find out pressure, temperature at each and every point. Okay, T01 is given, T01 will be given, and R will be given, pressure ratio across the compressor. Okay, so the data will be T01, T01, and
Sir?
yes.
So due to change in the temperature, or we can say due to reversibility, so the pressure ratio will also change.
Due to?
So pressure ratio will also change here, no?
Pressure ratio, no, I am using a compressor for a particular pressure ratio.
Sir, if the temperature will change, then T02 T02 will be greater than T02 dash, then the pressure ratio will
Yeah,
change.
T02 will be more than T02 dash.
So pressure ratio will change, sir.
No. I am compressing from this line to that line. I am going straight or inclined. That is the difference. But pressure P02 is same line.
Okay, sir, understood.
Here, this is P02
Yeah,
line.
understood.
This is P02. Okay. So P01 will be given. P02, T01 will be given. RC will be given. T03 will be given. Okay. These are the main parameters. And in addition to that, if it is practical cycle, you will be given compressor efficiency, you will be given turbine efficiency. Okay, so I have to, because at 1 I know both of them, I have to go to 0.2. So RC is equal to P02 by P01, or P02 is equal to RC into P01. Okay, P02 is obtained. I have to get T02. So to get T02, first I have to get T02 dash using isentropic relation. So T02 by T02 dash by T01 is equal to P02 by P01 to the power of gamma minus 1 by gamma A minus 1 by gamma A, or RC to the power of gamma A minus 1 by gamma A. So what is that I will get? T02 dash I will get. And P02 dash is P02 only, because both are on the same line, 2 dash and 2 not. And so now T02 is to be obtained using compressor efficiency. T02 dash minus T01 by T02 minus T01. This will give me T02. Okay, this is the way from 1 to 2 I have to go, and I have to get the values at 0.2 or not 2. Is it clear?
Yes, sir.
In the same way, I have to do for turbine. Okay, so if I go to turbine,
Sir,
yes,
sir, the temperature is changing, but the pressure is remains constant. So other properties will vary according to that.
yeah. Okay, as the equation of state will give you rho.
Yes, sir.
Okay, so here in the turbine, if this is not 3, this is not 4 dash ideal, actual will be not 4 dash should shift to the right. Okay, so
With increasing entropy.
increasing entropy, right? But here what happens, previously compressor I have to give some work, but I have to give more work because of the friction. In the turbine I am getting work, this is ideal work, this much I have to get, W ideal. But in actual, because of the friction, I am getting only this much. It will reduce. Am I right?
Yes, sir.
Yes, sir.
So W ideal is equal to CPG into T03 minus T04 dash, and W actual is equal to CPG into T03 minus T04, which is less than W ideal. And so efficiency of the turbine is W actual by W ideal. Less by more, right? We are getting less. So CPG into CPG gets cancelled. So T03 minus T04 by T03 minus T04 dash, like this. Okay. So if I want delta T034, this is a turbine temperature change. So this is nothing but eta T into T03 minus T04 dash. If I take T03 out, This is 1 minus T04 dash by T03. This is efficiency T into T03 into 1 minus like this. This is turbine pressure ratio. Turbine pressure ratio and compressor pressure ratio are same in ideal cycle, but now it is not. I will show you why. Turbine pressure ratio, I am writing RT. So T03 by T04 dash is equal to RT to the power of gamma G minus 1 by gamma G. So that I am putting here. So this is the way I can get this. So turbine work is equal to CPG delta T0 34. Like this. And so usually you will be knowing T03, P03, P04, you know. So okay, when we do calculations, we'll understand that. Okay, this is the way I have to do. So how to implement the losses in the compressor and turbine? This is the way. So efficiencies will be given to you. If they are not given, you can take it as 100% efficiency, like ideal one. But if you are given, you have to implement it this way. Is that clear?
Yes, sir.
Okay. And so we have implemented this. Then I want to talk about pressure losses. So there will be pressure losses everywhere in the combustion chamber. There will be heat exchanger. There will be, and intercooler. There will be pressure losses. Reheater. There will be pressure losses. Heat exchanger. There will be pressure losses. At combustion chamber, there will be pressure losses. So I have to consider all of them, and based on what data is given, I have to implement them. Okay. Now suppose I am giving the bigger one. I have intercooler, reheater, like this, and I have heat exchanger also, and I have to consider the pressure losses. There will be delta PIC, pressure losses in the intercooler, delta P RH, pressure losses in the reheater, delta P combustion chamber, sometimes they will give B, burner, okay, delta PB or delta PCC you can write, and delta P on the heat exchanger on the air side, delta P heat exchanger on the gas side. So from here to here on the air side there will be some pressure loss. From here to here on the gas side there will be pressure loss. And in the intercooler there will be pressure loss. In the reheater there will be pressure loss. So how to implement this? So what happens is, when I draw the actual cycle, it will be something like this. So first compressor, it is compressed like this. When it is coming like this, I lose some compressor, the pressure ratio. So if this is 1, and suppose this is 5, 6, some 2, like this, if I have, okay, here there will be instead of coming in this line, it is coming at a lower line. So some pressure is lost. So delta P intercooler, I am writing all not 1, not 5, not 6, not 2, okay, is equal to P05 minus P06. Is it okay?
Yes, sir.
And from 2 to 3, when it is going, there will be heat exchanger and there will be combustion chamber. So there will be some pressure loss in the heat exchanger, and there will be some more pressure loss in the combustion chamber. It will go like this, not 3. So P06 is equal to P05 minus delta P interpolar. Okay, if I want pressure here, I have to reduce the pressure here like this. Similarly, if I want P03, I know P02 minus, this is delta P heat exchanger air side. This is delta P in the burner or combustion chamber. So delta P HA minus delta P B, like this. Is it clear?
Yes, sir.
And then in the first turbine, then reheater, when it is going, here also I lose some heat. Suppose if I put here 07 and this is 08, and this will be delta P reheater. So P08 is equal to P07 minus delta P RH, like this.
Sir, in the second compressor and the intercooler, there also be some pressure loss, na?
In the intercooler, in the intercooler, there is pressure loss here I am showing.
And second compressor, sir.
No, in the compressor, there is nothing like here efficiency due to friction will be there. So here it goes like this. It goes like this. And it goes like this because of the efficiency. Is it clear?
Yes, sir.
And here, what happens is, here there will be, actually it has to come like this with P01, okay? But there will be, instead of coming out with atmospheric pressure, it has to come with higher pressure because it has to go through heat exchanger, right? On the gas side. So what should, it should be more than P01 like this. This is 04 and this is delta P Hg. So P04 is equal to P01 plus delta P Hg. I cannot expand it up to P01. Actually, I have to expand it till the atmospheric pressure. I will have more pressure ratio. But because I have to push it through heat exchanger, I have to have higher pressure than atmospheric pressure. Then only it can go through heat exchanger. Am I right?
Yes, sir.
So that's why P04 is equal to P01 plus delta P Hg. Okay, so this is the way various pressure losses are there, which are to be implemented based on what are given. If some are not given, you need not worry about it. But in the problem, whatever is given, you have to implement it. So this is the way I have to implement the pressure losses. Is it okay?
Sir, can we relate delta P of HA and delta P of HG?
Yeah, delta P HA. See, the air is going from 2 to, okay, here it is, it comes something like this. It goes something like this. Okay, here it is, I'll put 09 and 10. Okay, in the heat exchanger, it is going from 2 to 9.
Yes, sir.
So here there should be some pressure loss will be there because out of compressor it is coming with high pressure, but when it is going through heat exchanger, it loses some pressure because a lot of pipings are there, right?
Yes.
So some pressure will be lost there. And after that, it goes through combustion chamber. There also some pressure will be lost. And then it goes to turbine. So when it goes to turbine, there will be some pressure loss in the heat exchanger on the air side and also on the combustion chamber, in the combustion chamber.
Sir, P09 point will be on the heat, sorry, the compressor side.
See here, from the compressor, it is coming with 02 and leaving at 09. And heat from turbine, it is coming at 04 and is leaving at 010. Okay, so 02 to 09, there will be some pressure loss. And 04 to 010, there will be some pressure loss. This is delta P Hg. This is delta P HA. Okay?
Yes, sir.
That's the way. It's okay now?
Clear, sir.
Yeah, there are some more things also. Mechanical efficiency. So here, I have compressor and turbine. You always remember compressor should be like reducing area, turbine should be like increasing area. Okay, this is running this. Okay, this needs some compressor work, WC. But from here to here, there is some transmission through shaft. There will be some losses will be there. Am I right? So I have to supply a little bit more work. Am I clear?
Yes, sir.
So network is equal to actually WT minus WC. But WC, if I just supply like that, it is not enough. I have to supply more work. So if mechanical efficiency is 99% or something, then WT minus WC by mechanical efficiency. This is the work that is taken by the compressor. More work to be given. Sometimes we call it as WTC. The work taken by the compressor from the turbine. Is it clear?
Yes, sir.
And similarly, when it is going to generator, right? So the network coming out of this is WT minus WTC. I got this. But again, here also there may be some transmission loss. Is it clear? So power this is to be power I have to get at the generator, but because of the loss, I have to multiply by mechanical efficiency. It will be less than whatever I am supplying from here. Am I clear?
Yes, sir.
So this is about mechanical efficiency. There will be what is called as combustion efficiency. Okay, so suppose m dot a mass of air is this much, and heat that is required is QH, which is equal to m dot a CPG. Suppose just like that I'm telling T03 minus T0. If I have only one combustion chamber, okay, this much of heat is to be supplied to the cycle. For this, I have to burn some fuel, right? So if fuel is mass flow rate of fuel, and how much heat will be supplied by burning this, I have to multiply by calorific value. So the heat input is equal to m dot f into CV. Okay, this much heat is to be supplied. This must be equal to this, but I may lose some heat during burning due to incomplete combustion. Am I right? So if this is eta B, combustion efficiency, I will get less than this. Okay, this is the heat that will be supplied. This will be QH. Is it clear? Because I need QH, and if I know CV, if I burn exactly that much of fuel, but I will not get that much because some incomplete combustion will be there. So though this is the theoretical input I am giving, but I will get less than that. So I have to multiply by combustion efficiency. Am I clear about it?
Yes, sir.
Yes, sir.
Okay, this is about combustion efficiency. Okay, there are some more things I will define like SFC. What is specific fuel consumption?
Sorry, amount of fuel required for
Mass of
unit
fuel
power.
for
Unit
Unit
works.
power output.
Okay, and power is mass of air into specific output, Wn, small w if I write, this is specific output into Wn. This is the total power. So that is m dot f by m dot a Wn. And F is fuel air ratio. That is m dot f by m dot a. So this is equal to F by Wn. And Wn is specific output. Specific output means kilojoule per kg, right?
kg.
Kilojoule per kg. And so here, what are the units of F? No units, right? Fuel air ratio. So what are the units of F by Wn? Kg by kilojoules, right? Am I right? Because Wn is kilojoule per kg. So kgs per kilojoule. So this is nothing but kgs per kilowatt seconds. But usually we want in kilowatt hours. So I have to multiply by 3600. So SFC is equal to 3600 F by Wn kgs per kilowatt hours. Right?
Yes, sir.
Actually, one more thing also is there. Many times we will neglect it. So here, the mass flow of compressor, if the mass flow of air is this much, for the combustion chamber, mass flow will be m dot a plus m dot f. Am I right? It is not the same mass flow. For turbine also, it will be m dot a plus m dot f. This much of air fuel mixture will go. But many times for turbines, the usual air fuel ratios are very high in gas turbines. How much it comes to? Approximately maybe 100. If air fuel ratio is 100, so F is equal to 0.01. Am I right?
Yes, sir.
So this m dot a plus m dot f, I will write it as m dot a into 1 plus m dot f by m dot a is f. Okay, so this f is 0.01. So whether I multiply mass flow by 1 or 1.01, the variation is very small. So f can be neglected compared to 1. And so the mass flow, I can take it as a uniform mass flow throughout. Is it clear?
Yes, sir.
Yes, sir.
But at the beginning of the problem, if I know mass flow of fuel ahead, I have to consider it. Otherwise, I can ignore it. Okay, so all these things you have to remember. And so if I just, if I want to solve a problem, okay, just, I'm giving just a rough data. Suppose T01 is equal to 300. T03 is equal to 1200. And pressure ratio is equal to 4 again. And so now these are the minimum things that are needed. Now for compressor, I will take a simple cycle without intercooler reheater. Okay, simple with heat exchanger.
Pressure at Mach 1, sir.
Yes, P01, 1 bar. Okay, so these are the things needed. And then compressor efficiency, I will give you as 0.85. And turbine efficiency, it will usually, turbine efficiency will be more than compressor efficiency. Do you know why?
Repeats the question, sir.
In compressor, there is adverse pressure gradient. Am I right? Pressure increase, right? So whenever there is adverse pressure gradient, there will be more losses. And in turbine, there will be favorable pressure gradient. That's why the percentage will be a little bit more. And mechanical efficiency, it will be 99%. There will not be much loss. Okay, it's very small. And the combustion efficiency, it is you can take 98%. And effectiveness of heat. Okay, this is another thing I forgot. Okay, effectiveness of heat exchanger, you can take it as 0.9. Okay, because there will be more pressure loss here. And then delta PB is equal to, usually it will be given like 0.04 bar or something, or you will be given like 3% of compressor delivery pressure. Am I clear? You know P02, so 3% of it will be lost, and P03 can be calculated like that. That is, P03 is equal to 0.97 P02. Am I clear?
Yes, sir.
Okay, so this is the way. Now what we have to do is, you have to get the power output and efficiency and SFC. Okay, these are the things you have to find out. This is the data you will be given. So point by point, you have to calculate. Okay, I have to put heat exchanger losses also. Okay, so delta P, because I am putting heat exchanger, right? So delta P HA, maybe you can take 2% of P02. And
So
delta,
air fuel ratio is not given.
yes?
Air fuel ratios are required na, for specific fuel consumption.
No, will be given, I will tell you. I will give calorific value. Calorific value is normally standard 143,100 or kilojoule per kg, or 43.1 megajoule per kg. Okay, this is calorific value. Okay, we will see what is to be done. Delta PHG, maybe you can take some 0.04 bar. Okay, so this is the way it is given. And so it will be like we will have delta PHA, then delta PHG. So this will be 0.3. This is 0.1. This is 0.2 dash. And this is 0.2. Okay. And this is 0.4. This is 0.4 dash. This is delta P HA. This is delta P B. This is delta P HG. And it comes like this, and it goes like this. So I will take this as 0.5, this as 0.6. Okay, 0.6 is not needed actually. We don't use that. Okay, so this is the way the figure is to be drawn. And point by point, I will quickly tell how to go about it. P01 is equal to 1 bar. P01 is equal to 300 Kelvin. Okay, so we go to first 0.2 dash, and P02 dash is equal to P02 is equal to R P01. R is known, P01 is known, so this can be calculated. Then T02 dash is equal to P02 by P01 to the power of gamma A minus 1 by gamma A. This will give you T02 dash. And then compressor efficiency is equal to T02 dash minus T01 by T02 minus T01. This will give me T02. And then compressor work is equal to CPA into T02 minus T01. Okay. And then 2 is over. I have to come to P3. Okay. So P03 is equal to P02 minus delta PHA minus delta PD. So this will be like here 3% and here 2%. 1 minus 5% means 0.95 P02. Okay. So here 3% and here 2%. 5% is lost. So P03 will be known. T03 is data. As it's 1200 Kelvin. So next I have to go to NOT 4. For NOT 4, first I have to go to NOT 4 dash. Can you tell me? I have to get P dash and P03. P03 is known. P04 dash is equal to P04 is equal to P01 plus delta P Hg. Am I clear?
Yes, sir.
Then pressure ratio or temperature T03 by T04 dash is equal to P03 by P04 into gamma G minus 1 by gamma G, which gives me what is the unknown here? T04 dash. Then I have to get T04. That I will get from the turbine efficiency. T03 minus T04 by T03 minus T04 dash will give me T04.
So here the pressure ratio taken same.
Pressure ratio?
We have taken same. Like sir, P03 by P04. P04 is given, sir.
P04 is not given. P04
Okay, sir. We will determine. Okay, sir.
So
Understood.
from P01 to I have to add P0 delta PHG to get P04.
Understood.
Okay. So then T04 I have to calculate. So I got all the pressures and temperatures. And one more temperature, T05 is needed. That is obtained from effectiveness. What is effectiveness of heat exchanger? Actual heat rise by ideal heat rise. And what is the actual heat rise?
T05
Minus T02.
minus T02.
Ideal one is?
T04 minus
T04 minus
T02.
T02.
So what is the unknown here? T05. Right? So I get all the temperatures. Once I get all the temperatures, WC is equal to CPA into T02 minus T01. And WTC is equal to WC by mechanical efficiency. And W turbine is equal to CPG into T03 minus T04. And W net is equal to WT minus WTC. Am I clear? And so here QH is equal to CPG into T03 minus T05. Am I right? Combustion chamber, it is from T05 to T03. Okay. And so here, if I want a fuel air ratio, so CV is given. So m dot F CV eta B is equal to m dot a 2h. And from this, I can find out what is F. 2h by m dot f Cv eta. No, m dot f will not be there. Is it clear?
Sir, turbine efficiency also include. We have not included, sir.
Oh, yeah. Turbine efficiency is included. See, previous one, here, to calculate T04, I have to use turbine efficiency.
Yes, sir. Yes,
Okay?
sir.
Yeah.
Yes, sir.
Okay, this is the way I get it. And, okay, this is fuel aeration. Okay, suppose now m dot a is not known. Sometimes it will be given that it is some power is equal to some 150 megawatts or something like that. Okay, so maybe in the data I
Sir?
can take like that. Yes.
Here, mass of the air will take or mass of the gas?
Yeah, mass of the air is taken to be mass of the gas. I have neglected, compared to that,
Okay, sir.
I have neglected that. So P is equal to, maybe I will take previous one. In the data, I will get power I will give you some 150 megawatts. It is a 150 megawatt engine. So with that, I can calculate what is the mass flow of air that is needed. Okay, so mass flow of air is equal to power by specific output. Am I clear?
Yes, sir.
So if I get this, I can get m dot f. What is m dot f? Because f is equal to m dot a by m dot f. So m dot a into f will give the mass flow of fuel. And then if I want SFC is equal to m dot f by P, 150 megawatts. And then efficiency, you can take it as power by the total input is m dot f Cv. Is everything clear?
Yes, sir.
Yes, sir.
Okay, this is the way you complete the calculations, right? And next class we will see the values. And because we have used only few of them, I didn't have intercooler, heater, reheater, all those things, and those pressure ratios are not included. There is one more thing is there. That is another important thing. It is what we are doing is what is called a single shaft engine. There will be what is called as twin shaft engine. Okay, what will it do is, previously, I don't know whether anywhere I have drawn it. Okay, here actually this is a single shaft. But now what I want to do is a twin shaft. Here this is one shaft and this is another shaft. It is not like that also, right? Just I will have two turbines. This running the generator, this running the compressor. Okay, this goes like this. This is connection somewhere. This is turbine 1. This is HP turbine. This is LP turbine. This is compressor. Is it clear, this one? There are two
Yes.
turbines. First turbine runs the compressor, HP turbine. LP turbine runs the generator. Like this. So this HP turbine produces work which is just sufficient to run the compressor. And the remaining work is from LPT that generates the power. This is what is called as twin shaft engine.
So we have to take the different work output of these also.
Yeah, this is called as power turbine. This is called as power turbine. And this is called as gas generator turbine. Okay. And HPT and LPT, they are not mechanically coupled. And these are aerodynamically coupled. There is no shaft, but there is a relation. Okay. So whatever is coming from HPT goes into LPT. This is aerodynamically connected, but mechanically not connected. And when I draw the TS diagram, it will be something else. It is split like this. Okay, so if I write not 1, not 3, not 2, not 3, not 4, not 5. Okay, and not 4 will be calculated from compressor work. Okay, so if I W turbine 1 is equal to WC1 by mechanical efficiency, and WC1 is CPA into T02 minus T01 by mechanical efficiency, and WT1 is CPG into T03 minus T04. So I have to calculate T04 from this equation. Okay, and from this I have to find out what is the pressure ratio needed by the first turbine, and remaining pressure ratio only is used for running the power turbine. Okay, this type of problem also we will do in the next class.
So pressure ratio, can you repeat once?
Okay, the pressure ratio of the first turbine depends on how much work is needed by the compressor. It produces the work just sufficient to run the compressor. So the pressure ratio that is needed, right, by the first turbine is fixed based on the compressor work. And the remaining pressure ratio is used for developing the power.
Yes, sir.
So I have to know what is the total pressure ratio, and out of that, if I know the used pressure ratio, unused pressure ratio only is to be used for the output. Okay, I have to find out the work here based on this pressure ratio that gives me net output. Okay, that we will do in the next class. As far as simple single shaft engine considered, everything is clear, right? Here.
So that means the second turbine will give the net output.
Yeah, only second turbine gives the net output.
Yes, sir.
Okay. That we will do in the next class. Any doubts? Any doubts? So otherwise, we will go for the story.
Yes, sir.
Okay. It is about one real story of one inspiring personality. He is Glenn Cunningham. I don't know whether anybody heard about him, but he's very, very popular, famous, and inspiring personality. And when once a young schoolboy was caught in a fire accident in his school and was assumed that he would not live. He's very much burnt. So people thought he will not live. And his mother was told that he was sure to die, for the terrible fire had devastated the lower half of the body, very much damaged the lower part of the body. Even if he were to survive, they told he would be crippled throughout his life. That's what is told. But the brave boy did not want to die, nor did he want to be a cripple. Much to be the amazement of the doctor, he did survive. Okay, so he survived. But unfortunately, from the waist down, he had no motor ability. He cannot move. His thin legs just dangled there lifeless. Ultimately, he was discharged from the hospital, but his determination to walk was indomitable. He wanted to walk, but anyhow, it's not possible. At home, when he was not in bed, he was confined to a wheelchair, either on the bed or on the wheelchair. But because of his determination, one day he threw himself from the chair. He cannot get down. Just he has fallen down and pulled himself across the grass. So he was dragging his body, dragging his legs behind him. He reached the picket fence behind the house and raised himself up. And then, stake by stake, he began dragging himself along the fence. He was dragging himself by catching the fence, and he was dragging himself. His resolve to walk was undeterred. And he did this every day. Okay, maybe first reading it is comfortable, but how much pain he has faced every day, you can just, if you imagine, it's amazing. He did this every day with faith in himself that he would be able to walk unaided. With his iron persistence and his resolute determination, he did develop the ability to stand up for many days after. And then he started to talk haltingly, then to walk by himself, and then to run. Right? So, but it took very long time. And he began to walk to school, then run to school, to run for the sheer joy of running, because he was told that he cannot run or walk. Now, once he learned running, right, he enjoyed running. Later in college, he made the track team. In February 1934, in New York City's famed Madison Square Garden, this young man, who was not expected to survive, who would surely never walk, he could never hope to run, this determined young man, Dr. Glenn Cunningham, ran the world's fastest mile. And it is the record, an epitome of the power of positive thinking and faith in oneself. Glenn Cunningham continues to be the inspiration of many, and his story a brilliant testimony to how one can bounce back even when all odds are stacked against one, to the extent that death seemed only the preferable option. So people thought you only die. Okay, other than death, there is no option like that. But he became like that. You can see him. Okay, this is the person. He says, in running, it is a man against himself, the cruelest of opponents. Actually, your main opponent is yourself only. The other runners are not the real enemies. His adversary lies within him, in his ability with brain and heart to master himself and his emotions. So that's what he says. He's a great guy. And he could run 1 mile distance in 4 minutes, 3 seconds or 4 seconds. And at that time, this is a record. And he wanted to beat himself to complete it in 4 minutes, but he could not do. That is a very popular 4-minute mile like that. And people thought it is impossible to run a mile in 4 minutes. But now the record is broken. Right? Now somebody has run in 3 minutes 47 seconds. But it took many years. For many years, Cunningham's record is the record. And later, now many people, it is like evolution, right? I believe in evolution. People say that as the time is progressing, people are becoming weak and weak, and now they are more weak because of environment or food or other things like that. But I never believe that. Always there is increase in the power, both intellectual and also physical. You can see that every record which is thought to be cannot be broken, now are broken. Every time there will be records broken. So how can somebody break old record? Because he is more powerful than the previous generation. Why people think like that is, in olden days, there is nothing much medicine and all, survival of the fittest. Only fit people used to survive, other people used to die. And because of that, all fit people are around, so people think that all are strong. But nowadays, because of the medical progress and all, people extend the life. The average life period is very much high compared to the olden days. And because of that, because they are extending the life like that, we see many weak people around. And because of that, we see that we feel that actually now the generations are weak. No, nothing like that. There are weak people are there, strong people are there, and compared to previous generation, always the strength, intellectual, psychological, and physical strengths always increase in evolution. Okay. Okay, this inspiring personality I wanted to share about him, and thank you very much. Any questions?
No,
Okay,
sir.
you go through the chapters, real cycles and practical cycles in Ganeshan, and also the gas turbine cycles from Sarvanamuttu. So these two books you read, and you go through the worked out examples, and you have to go through the exercise problems also. So you are going to get in the mid exam and the final exam the problems from mainly these books only. You have to have a lot of practice. And because these problems are very tricky, if you do one mistake at the beginning, right, the complete problem will be wrong, because everything step by step, right? If your T02 is wrong, then P02 is wrong, or then 3 values, 4 values, 5 values, all will be wrong. And the complete problem will be wrong. And for procedure, there will not be much marks, because all people know the procedure, it is obvious thing. So numericals are important. So unless you do practice, you are bound to do some mistakes. Okay. So for CPA, you may put CPG. You may forget about CPA. When you put CPG, you may forget and you put CPA. So like that, and there will be a lot of change in the values. Okay. So you need practice. And it is not just reading. It is not enough if you know the procedure. You have to practice it. Okay.
Sir, can you repeat the
Yes.
books and the topic from which we have to practice?
Ganeshan and Sarvanamuttu. These are only two books. Ganeshan book, there will be real cycles one chapter, practical cycles one chapter, I think. In the Sarvanamuttu, I think there is only one chapter for all gas turbine cycles, both ideal and real. There is nothing like ideal cycle chapter there. There is only one chapter. In Sarvanamuttu, shaft power cycles, one chapter is there, second chapter. Okay, first chapter also you go through, because it gives all different models of the aircrafts, different engines and all those things. It gives a lot of general information, right? General idea. So you go through that chapter, and then shaft power cycles is the one which we have covered. You have to solve those exercise problems, go through example problems, and you have to try for exercise problems. Any doubts we can always discuss. And Ganeshan, I think first two are second and third chapter. I don't know. There is one chapter on ideal cycles, one chapter on practical cycles. Okay, stop recording.